Hello everyone and welcome back. Today we're going to talk about a very specific type of problem. It is also a very common problem that you will run into, and I simply call it the sign problem. Here's the situation. Over here we have a wall. Attached to the wall is a hinge right here with a pin right through it. Attached to that is a metal bar or a bar of some kind. There is a string attached from the end of the bar to the wall over here, and from the bar you hang a sign. This is something you would see in front of stores and such. So hinge, bar, sign, rope, wall. And of course the rope or string is going to have a tension in it. Here are the questions for today. And as I said, they are very common questions for this problem. 1. What is the tension in the string? 2. Was the net force exerted by the hinge on the bar? And 3. Will the tension increase or decrease if the attachment to the wall is lowered? All right, we're going to handle these one at a time. And we're going to start with the first one. What is the tension in the string? Let's start out with some basic information. I'm going to say the weight of the bar is 120 newtons. And the weight of the sign is 600 newtons. I have my measurements 3.2 meters from the wall to the string that holds the sign, and another 0.8 meters from there to the edge of the bar. This is important because the string that attaches to the wall is also at the edge of the bar. And from the hinge, and the string is attached 2.5 meters above the hinge. So you may have noticed you have a nice clean right triangle here, which we are going to make use of. Now, let's go to answering my torque questions. Number 1, is the system in equilibrium? Well, the answer is yes. Nothing here is moving. No one hangs a sign in front of their storefront that's going to fall down on people's heads. So this thing is not moving. 2, where is the axis? Well, considering we have the weight of the bar and the sign, there's no reason not to put the axis right where the hinge is. In fact, it benefits us because we know almost nothing about that spot right now. And if we put the axis right there, in terms of torque, we don't have to worry about it because there would be no radius. 3, how many non-zero torques exist? Well, let's find out. Number 1, earth on bar. We have a force earth on the bar, which is going to be downward. Now, the bar is considered to be a uniformly distributed object, which means I'm putting this arrow dead center of the bar. If I have 3.2 meters here and 0.8 meters here, that means this is located 2 meters from the wall, and the weight of the bar is 120 newtons. We also have the sign. Force earth on sign is 600 newtons, which is going to be the tension in this string, which means the force is at this very specific location on the bar that is 3.2 meters away from our axis. And there's also a third torque. That third torque is going to be from the string. We have a tension in the string going this way, but that means we have a perpendicular component and we have a parallel component. In fact, I'll just call this force perpendicular and force parallel. And I'll call this tension 1. This is what we're after right now. While I'm here, and something else I mentioned earlier you may notice, this makes a nice big right triangle. And if I now recognize I have a tension, and that tension, which is a vector and is also at an angle, the first thing we're going to do to it is break it up into its component pieces. And to do that, I need to find out information about these right triangles here. Well, I can start doing that pretty easily because I have dimensions here and here. If I'm looking at this angle here that I've labeled alpha, I can find it using inverse tangent. Alpha is inverse tangent, opposite of adjacent, which is 2.5 meters, over 4 meters, which is about 32 degrees. Now, since I'm going to be working with the forces here, I'm going to be more interested in this angle here that I'll call theta. And if alpha is 32 degrees, that means theta is 58 degrees. All right, now that I've identified that, I still have a problem. I don't know what these are. And I also know I'm tension 1, which is our goal. So at this point, we're going to put up our table. And we're going to answer our third question. How many non-zero torques exist? Well, we have 3 of them. One here, and one here. Remember, only the perpendicular force matters. I'm going to name them from the inside out. I'll call the first one B for bar, the second one S for sine, and the third one I'll call tension perpendicular because it is the perpendicular of the tension force. It doesn't really matter what you name them, just so you can recognize what's what. And again, since the system is in equilibrium, the total down here for the torque should be 0 Newton meters. Okay, next up, let's identify directions. The bar and the sine would swing this thing clockwise. Therefore, bar and sine are both negative. Tension would swing it counterclockwise, which unit circle is positive. And they'd all equal 0. All right, let's start filling in. Force from the bar, 120 newtons. Radius for the bar, the hinge to the center of mass of the bar, is 2.0 meters, which gives us negative 240 Newton meters. Force for the sine, 600 newtons. Radius for the sine, 3.2 meters, which gives us a torque of negative 1920 Newton meters. Force for the tension, unknown. Radius for the tension is going to be 4 meters. Now, we don't know the torque, but we do know this has to add up to 0. If these two are negative, they combine to 2160 Newton meters. Now this equals 0. Using my torque equation over here, if I know the torque, I divide by the radius, which is 4 meters, I will get the force. And that would mean our force is 540 newtons. That is the perpendicular force from the tension. I will put that here. Now, our job is not done. This is the perpendicular component. We need the actual full component of the tension. Fortunately, we have the angle that's right between them. In other words, this makes a nice right triangle here. Since I have the adjacent side and the angle and I want the hypotenuse, we are going to use cosine. Cosine theta is adjacent over hypotenuse. Therefore, hypotenuse is adjacent over cosine theta. 540 newtons over cosine 58 degrees gives us 864.2 newtons. That is the tension in the string. So notice I use my whole system here. The biggest thing is recognizing what you have and keeping it organized. Is it in equilibrium? Yes. Where's the axis? Right here. How many non-zero torques exist? This is a very, very important question to answer. That is what allows you to make the table and put everything together. The rest of it's like filling the missing pieces of a puzzle. All right, that answers question number 1. What is the tension in the string? Now we're going to go for what is the net force exerted by the hinge on the bar. Here's what that means. There's a pin that goes right through the hinge and right through the very edge of the bar. This string is not the only thing holding up that bar. The hinge is doing so also. But we have another issue where this tension is exerting a horizontal force into the wall. Now, if the system is in equilibrium, that means net torque and net force is 0. So if something is pushing left, something is pushing right. And that thing that is pushing right has to be the hinge. So what we're going to have here is forces on 2 axes that we're going to have to put together. Let's do the horizontal first. And I'm going to make a little start point here for my vector addition. To bring them back, force earth on bar was 120 newtons. Force earth on sine is 600 newtons. And force perpendicular was 540 newtons. Let's start with the horizontal axis. Horizontally, there is only one force pushing to the left, and that's force parallel from the tension. And we can get that easily enough using tangent, because we already have the adjacent side. If tangent is opposite of adjacent, then opposite is adjacent times tangent theta, where theta again is 58 degrees. Now we're expecting a larger number because 58 degrees is larger than 45. In other words, the opposite side should be bigger. 540 newtons times tangent 58 degrees gives us 864.2 newtons. Therefore, the force to the right from the hinge has to be 864.2 newtons to counteract the force from the left, which I'll put here. Okay, how about the vertical force? Well, that's even easier. This bar is not moving, therefore all horizontal forces must cancel, and all vertical forces must cancel. Right here, I have 600 plus 120 newtons downward, which is a total of 720. However, I only have 540 newtons upward. Therefore, there must be a missing upward force. Since the forces must balance, there must be an upward force of 180 newtons. In other words, 180 plus 540 newtons upward has to equal 600 plus 120 newtons downward. Up and down both equal 720, which ensures the system is in equilibrium. Now, what we want is this one, and this angle that I'll call phi. Because remember, a vector requires a magnitude and a direction. I'll call this force hinge on bar, and I will simply use Pythagorean's theorem because I have both sides, where this is obviously a right angle, and that gives me 882.7 newtons. So I'll put here. We also need phi, and to do that, I'll use inverse tangent, opposite over adjacent, 180 newtons over a 64.2 newtons gives me 11.8 degrees. So my full answer, which I'll put in the lower left-hand corner because I'm running out of space, would be 882.7 newtons at 11.8 degrees above the horizontal or above the positive x-axis, which would be approximately this way. So in other words, I have two forces pulling down on the bar, two forces pulling up on the bar. It would be a component here, and they would be equal vertically. I have one force pulling to the left and one force pushing to the right. Again, it's a component, and they would be equal. So the combined force from the hinge on the bar would be 882.7 newtons at 11.8 degrees above the positive x or above the horizontal. All right, let's answer our third question. Will the tension increase or decrease if the attachment to the wall is lowered? So what this is asking is, if I take the string here and lower it to, say, this position down here, what would happen to this tension in the string? Well, all we really need for this is some conceptual trig. To help you see it, let me actually move this on the side for a bit. I will put it here. So if the string was to be lowered, this horizontal component would need to be larger. It's kind of like opening the mouth here. Since the vertical component must stay the same, something must get bigger. The horizontal part has to get bigger, and if one component of a right triangle gets larger, that means the hypotenuse must get larger with it. So if you're the one hanging this sign, you need to be careful of having this too low, otherwise the tension could be so large the string could snap. The higher you place the connection to the wall, the lower the tension is going to be. So if you were to put it up here, the tension would be lower than 864.2 newtons. Basically put, as long as you're within the tension limit of the string, however, you are fine. Okay, I wanted you to show this one because, again, very common problem and three very common questions that go along with it. All right, I'm going to end here. Have a good day. This is Mr. M, signing off.